Previously in chapter 4, we learned about the concept of forces. Then we move back to chapter 3, where we learned about the idea of impulse and momentum. And now in chapter 5, we are going to explore a new concept, which is work, energy, and power. So this video will be a rough overview for chapter 5, and I'll base this overview here, base it on chapter 3. Because later, as you can see, chapter 3 and chapter 5 share great similarity in terms of the way they are being structured. So let's get into it. So in chapter 4, you learn about forces. You learn about the 5 different types of forces that you can observe in macroscopic nature. Then you also learn how to illustrate all the forces acting on an object using a free body diagram. Then you move on to learn about the 3 Newton's law of motion. The first law of motion used for situation where you have no net force acting on an object. The second law of motion is for situation where you have a net force causing an acceleration. For the third law of motion, you learn about action-reaction pair, where if you have object A exerting a force on object B will also exert a force back on A. And these two forces form a pair, and they should have equal magnitude and opposite direction. So that's the Newton's 3 law of motion. Okay, Newton's law of motion. So from chapter 4, we move on to chapter 3. Okay, we move back one chapter to study chapter 3. And in chapter 3, we create a new physical quantity, which we call it as impulse. As you can see, impulse here, it's a multiplication of the average force with the time interval in which the average force is being applied on the object. Okay, so now as you can see in this equation here, we introduce the concept of time into the discussion of forces now. Previously in chapter 4, there was no discussion about time. Everything is just at that particular moment. But now we bring in the concept of time. To be more particular, we bring in the concept of certain time period into the discussion of force. So chapter 3 is for us to study forces being applied over a certain time period. What is the impulse and what is its effect? Okay, so why do we need to create this new physical quantity? Because this physical quantity impulse here actually tells us something about the motion. Okay, so let's try and see what kind of properties does this impulse tells us. Okay, so from impulse momentum theorem, we know that if we are able to calculate impulse, we will know the change of momentum that happened to the object over that time period. So let's say if you determine the impulse acting on an object over the time interval of 0.5 seconds, it's 5 Newton second. Let's say, okay, the impulse is 5 Newton second. Then you know the change of momentum that happens to the object over the course of 0.5 seconds will be 5 Newton second. So that's impulse momentum theorem. So you can see here, this impulse here is related to force, so it represents the cause of motion. Whereas this change momentum is a product of mass and velocity. So by knowing impulse, the cause of motion, we can relate it to the change momentum, which we can further relate to the change of velocity, which is the motion itself. So you can see this equation here forms a cause and effect kind of equation, because the left hand side shows the cause of motion, which is related to force, the impulse is related to force, but for the right hand side, it represents the effect, which is the motion itself. And what properties are being observed? The velocity, the change in velocity that happens to the object. Okay, so this is impulse momentum theorem. So once we have learned it, we move on to study the principle of conservation of linear momentum. So conservation of linear momentum says that the linear momentum of a system will be conserved or will not change under a certain specific condition. So when the linear momentum does not change, then the total momentum of the system initial will be equal to the total momentum of the system final, because it does not change. So what is the specific condition in which linear momentum is conserved? Linear momentum is conserved for an isolated system. So what is an isolated system? We say isolated system is a system where the sum of external force acting on the system is equal to 0. Sum of external force equals to 0. Well, this sum of external force, is actually quite different from the external force that you learned in chapter 4. In chapter 4, the external force that you learn are forces that you cannot classify as gravity, cannot classify as normal, cannot classify as tension, cannot classify as friction. So those things that can't be classified into these 4 types of forces, we call it external force, or usually the force that is being explicitly mentioned in a problem or in the problem statement. Okay, but for in this case, for isolated system, the sum of external force, this external force is the force that is exerted by something outside the system onto the system. Okay, let's say if we give an example, let's say object A and object B are colliding together, then comes apart like this. Okay, so in this case, what are we interested in are object A and object B. So object A and object B forms the system, and anything else which is not object A and object B will be our surrounding. Okay, so when we say external force, it means this external force is exerted by something which is not object A, which is not object B, on object A and object B. Let's say when object A and object B collides together, at that moment you are near the surface of Earth. So there's gravity pulling the object A and object B down. So the weight is exerted by the Earth on the two objects. So it's exerted by something external to the system onto the system. So this kind of thing we call it external force. Okay, so we can have external force acting on an object, but the sum of external force have to be equals to 0. Then the system will be isolated. Then when the system is isolated, sum of external force equals to 0. Then this we can put in 0. Then our impulse will be 0. If our impulse is 0, our change of momentum will be 0. Therefore, the linear momentum will be conserved. Well, this whole story is not that simple. We have to involve internal forces, external forces, and you have to involve Newton's third law of motion in the whole derivation process. But the simple way of thinking about it is J equals 0, therefore delta P equals to 0. Therefore, it's conserved. Okay, so how do we apply this conservation of linear momentum? We can use it on an equation like this. So let's say your system consists of object 1 and object 2. So what I can do is you find the momentum for object 1, sum it up with the momentum of object 2. Then this value will remain constant throughout the whole event. So m1u1 plus m2u2 will be equals to m1v1 plus m2v2. As you can see here, this u and this v here are vectors. So if we want to apply this equation in a 2D situation, we have to change this vector u and v here into its respective components, means by ux, uy, vx, and vy. So you have to break this vector equation here into two different equations, m1u1x plus m2u2x equals to m1v1x, m2v2x. That's first equation. Then the second equation, you can do it for the y dimension. So from there, you are able to analyze situation where the linear momentum is conserved for a 2D system. Okay, so these are the 3 important themes that we will encounter in chapter 3. And we are going to see that chapter 5 is actually structured in a similar manner. So let's go to chapter 5. In chapter 5, we also create a new physical quantity, and that new physical quantity, we call it work done. So work done here will be the dot product or scalar product for force and displacement. So instead of putting in time, instead of introducing time, now we are putting in displacement. So chapter 5 is suitable for us to analyze, suitable for us to use when we analyze system where forces are being applied over a certain distance. So last time it was certain time period, now it's over a certain distance. Then you can calculate this value, work done. Okay, work done is an important value because it also tells us something about the properties of the motion. Means by work done here is related to force, it's the cost of motion. And this value work done here also tells us something about the motion. So what does it tell us? Let's see. So in work energy theorem, we find that if we sum up all the work done by all the forces acting on an object, if we sum up all the work done, you'll find that this value here will be equal to the change of kinetic energy that happens to that object. So work total, the total work done here is related to force, so it represents the cost of the motion. Whereas the change of kinetic energy here, kinetic energy is half mv squared, right? So this kinetic energy can be related to speed. So from there we can see that something about the cost of motion will tell us something about the motion itself. It tells us about how the speed changes throughout the motion. So work energy theorem is important because it's a cause and effect equation. Then after we studied that, we also learned about something will be conserved in chapter 5. So what is being conserved is mechanical energy in chapter 5. So in what specific situation do we have our mechanical energy conserved? Well, that one is a bit complicated and you have never really learned it in depth before, but I'll just briefly tell you how we determine whether mechanical energy is conserved or not. Well, we learn about the idea of conservative and non-conservative force, and you see that if for a system, for an object, the non-conservative force does zero work on the object. If the non-conservative force does zero work on the object, and using the idea of work energy theorem and potential energy, we will be able to derive the equation to show that mechanical energy is conserved. So the mechanical energy initial will be equals to the mechanical energy final. The mechanical energy remain constant throughout the motion. So we can break down mechanical energy into kinetic energy and potential energy. And potential energy can be due to gravity or due to certain springs or elastic material. So you can find that initial mechanical energy is the sum of kinetic energy and potential energy for the initial situation. And the mechanical energy final will be the sum of kinetic energy and potential energy for the final situation. So from there, you see something is being conserved as well, similar to what we learned in chapter 3. But here, this is a scalar quantity, whereas for linear momentum, it's a vector quantity, which we need to break it down into x and y. But for mechanical energy, you don't need to break it down into x and y. It's a scalar quantity. Okay, so now you see there's a similar structure in the way how chapter 3 and chapter 5 is being structured. You create a new physical quantity, then relate the physical quantity as the cause of motion, then you study what is the effect. Okay, what can you observe? What kind of change can you observe to the motion? After that, you learn that under a specific situation, some kind of properties will be conserved. In chapter 3 is linear momentum conserved. In chapter 5 is mechanical energy conserved. Okay, but for chapter 5, we have another section which cannot be found in chapter 3. In chapter 5, we'll also learn about the concept of power, and power will be the rate of work done, which is this work done over here. How much work is done over every single unit of time. That's the rate of work done. And we know that work done here can be calculated over a certain time period or calculated over a specific moment. So if it's for a certain time period, it will be average power. If it's for a single specific moment, there will be instantaneous power. Okay, so that is the rough overview for chapter 5. And for the following videos, we'll be following this sequence. We will first learn how to calculate work done and what's the meaning of work done. Then after that, we relate the idea of total work done to the change of kinetic energy using the work energy theorem. So after we have done these two things, we'll learn about the idea of conservative and non-conservative force. And we also use the concept of potential energy and kinetic energy to derive the conservation of mechanical energy. And from there, we will apply the conservation of mechanical energy in various situations in which the mechanical energy is conserved. Lastly, we'll move on to talk about power, and we'll try to analyze a situation to study its average power and its instantaneous power. So that is a rough overview for chapter 5.